Hello, Manshu, am I audible?
Yes, sir.
Okay. So, guys, we are going to start the lecture very soon. We will wait for other students to join. So, till then, kindly draw the diagram which is shown on the screen. So, students, now I am going to start the lecture. A very good afternoon to all of you. There was a slight change in the timetable today. I feel sorry for that because I was in the dilemma that my lecture would start at 3:30, but unfortunately, the actual thing was based on our previous talks, it was being shifted to 1:30. So, sorry at the initial movement. I'm going to start the lecture very soon, and in the lecture, what I'm going to deal with you today is regarding the hybrid pi capacitances, validity of hybrid pi model, and variations of hybrid pi parameters. So I hope all of you have drawn the diagram that is being displayed on the screen. I hope my voice is audible and the screen is visible to all of you.
Yes, sir.
Basically, the hybrid pi capacitances is broadly classified in two categories that we have already studied. One is known as transition capacitance and the another one is known as diffusion capacitance. They are commonly known as CC and CE. Initially, they are basically known by CB-C and CB-E. B dash is the virtual base of the transistor, which we are considering at higher frequencies for hybrid pi models. I hope this is very clear to you because this is already being discussed. Yes or no? Please respond.
Yes, sir.
Now, coming to the main topic of diffusion capacitance, that is CE. Now, we know that when our in the transistor, if we talk about junctions, there are two junctions, one is JE and one is JP. In JE junction, if it is being forward biased, then we always say that the diffusion capacitance is quite larger than transition capacitance. If my diffusion capacitance is larger than my transition capacitance, then CE is approximately equal to CDE directly. Okay, can I proceed further?
Yes, sir.
Now, as you can see in the graph, there are two things. One is at x is equal to 0 and one is at x is equal to w. There are two things written on the top, that is emitter for E and collector for C. Now, the meaning of this particular graph is that P dash 0, the value P dash 0 is nothing but it is varying almost linearly. It is varying almost linearly from P dash 0 to 0 point, from top to bottom with a linear line, as you can see. So what it is that we are going to discuss today first, as the figure suggests is basically the minority carriers charge distribution in the base region. The figure gives the injected hole concentration. I do not need to explain you what is hole and what is electron. What do you mean by hole electron concentration? That is already known to you. Am I right? Am I wrong?
Yes, sir.
Yes,
Yes,
sir.
sir.
So based on the distance in the base region of a transistor, PNP specifically, the W is varying. What is the W? W is basically known as the base width. You can write down W is nothing but the base width. It is quite small as compared to the diffusion length. This diffusion length can be denoted by L subscript B, B for Bombay and L for Lucknow. So L subscript B is nothing but the length of the diffusion for minority carriers. As we were discussing, if it is a PNP or NPN transistor, or rather in broader sense, if it is a transistor, then there are two junctions. One is JE junction and another one is JC junction. I repeat, one is JE junction and another one is JC junction. So presently the condition is my JE junction is forward biased. If my JE junction is forward biased, then what happens is my JC junction is reverse biased. JC means junction at collector, JE means junction at emitter. So if my JC is reverse biased, then what happens? The charge concentration, that is P dash, is at 0 point. So as you can see in the graph, I repeat, as you can see in the graph, from this point to this point. So this is the charge concentration is 0 at collector point. Why? Because JC is reverse biased, whereas JE was forward biased. So all the charges were in the extreme level concentrated over here. I hope this point is very, very clear to all of you.
Yes, sir.
Yes,
Okay.
sir.
Now the W, which is known as the base width, is very, very less as compared to the length of the base. So W is less than LB. So what happens is this P dash is linearly varying from the top to the bottom, that is to the value 0 of the collector. Hence, we say that, I hope all of you have drawn the graph so I can proceed further.
Yes, sir.
Yes, sir.
Yes, sir.
So if W is very, very less than LB, we say that P dash 0, which is at the emitter side, is moving towards the point 0, which is at the collector side. So we say that QB, what is QB? That was in the shaded region of the graph. So QB is equal to half P naught dash A W into Q. Now over here, there are certain terminologies which you do not know. So all of you are requested to note down equation number 17. All of you are requested to note down equation number 17. 1717. Hello students.
Yes, sir.
So the QB was the portion of the shaded region in the graph. W is nothing but the base width. LB was nothing but the length of the base, half multiplied by P dash 0 is nothing but known as average concentration. Now this concentration we all know it is of minority carriers. So average concentration is denoted by half P naught dash. A, capital A is nothing but the base cross sectional area. The overall cross sectional area is being denoted by of the base is denoted by A. Hence W into A. W was base width, A is the area. So area multiplied by base width would give me volume of my base. WA is nothing but volume of my base. So guys, X1 is nothing but average concentration. X2 is base cross sectional area. W we already know that is base width. AW becomes volume of the base, and Q is very well known term, that is the charge of electrons. Yes or no? Can I proceed further?
Yes, sir.
Yes, sir.
I hope you have noted all the fundamental terminologies along with the formula, which is equation number 17. Please note down the next equation, that is equation number 18. I hope my message was being sent to all the class fellows that at 3:30 my lecture is there.
Yes,
So
sir.
within the class that topic might have been discussed. So that's good and fine, because I can see less number of students. That is why I just wanted to inquire about it. So now I'm going to start with I. Capital I is nothing but known as diffusion current. Capital I is known as diffusion current. So the differential part of my P dash, that is the average concentration of minority charge carriers, dP dash upon d of x, is commonly known as P dash 0 divided by W. Hence, from equation number 17 and equation number 18, if I combine both of them, QB would be equal to something like this. Do not worry about the terminologies for this particular article, it is not so important. Wherever it is important, I will let you know. Only I have put 17 and 18 all together, so QB becomes IW square upon 2dB. So that is not so much important, so you can just skip it out. But yeah, the final conclusion of this article is quite important, which would be the base of the next topic. Hence, based on this, I would like to move further. The diffusion capacitance for CE amplifier, that is CDE, is commonly known as dQB by dV. That is the differential part of this whole portion with respect to V. So this becomes something like this. As a result of this, we can say that this is this, where and how it is done, that is quite challenging. So we will understand how and where we have put the values. Basically, RRE, that is the emitter resistance, is denoted by dV upon di. Is denoted by dV upon di. So RE is also known as VT upon IE. RE is also known as VT upon IE, and the reverse of RE is nothing but GM, that is transconductance. reverse of Gm is this. That is why we have written the answer in such a way. The final conclusion that we conclude from this article is only one thing, and that is this. CDE is directly proportional to the emitter bias current IE. That's it. I wanted to say that in case of a emitter bias circuit or in case of a common emitter configuration at higher frequencies, considering the hybrid pi model, we can say that my IE is directly proportional to CDE. That is, my diffusion capacitance present in the circuit would be dependent on the output, on the not the output, but on the common emitter, that is IE current. That is the final conclusion. So now based on this hybrid pi model, we are going to understand what is the validity, what is the awareness, what is the ground truth reality about the hybrid pi model. So now I would like to focus on few more points. The graph that you had drawn had certain initiative points that I would like to focus upon. But before that, I would like all of you to kindly note down validity of hybrid pi model. Validity of hybrid pi model. Now we know that VBE. What is VBE? Any idea? VBE. Hello, students.
Voltage across emitter and base.
Good. So VBE changes slowly with time. That means what? If VBE changes slowly with time, that means the minority charge carrier distribution in the base is always a triangular graph. Is always a triangular graph. As you can see the graph, at x is equal to 0 and at x is equal to w, the slope would remain the same. The slope would remain the same. I mean to say that IC is equal to IE because IB is very small. So we say that in case of hybrid pi model, IC is equal to IE because slope at x is equal to 0 and slope at x is equal to w remains the same. Hence, are you noting it down or should I repeat it again?
So please repeat it.
Okay. Slope at x is equal to 0 and slope at x is equal to w is same. So IC is equal to IE. IC is equal to IE.
Noted, sir.
In case of hybrid pi model, I repeat, in case of hybrid pi model, under dynamic conditions only, rate of change of VBE, rate of change of VBE is so small, that IB base current IB is
सर इज के बाद इज सोर्स
is so small, એટલો નાની વેલ્યુ છે જેના લીધે IB ની વેલ્યુ બહુ નાની થઈ જાય છે as compared to IC is so small that IB is small than IC. IB is small than IC. Okay, are you getting it?
Yes, sir.
So based on the formula, we are moving further. Please note down this thing. So if I calculate it in a straightforward wise direction, I will say that W square upon 6 dB is equal to CE upon 3 GM. GM is my transconductance, CE is common emitter configuration, 1 upon 6 pi F of T. So 2 pi F multiplied by this value is lesser than 1, hence F is less than 3 of FT.
Sir,
So,
oh,
एक मिनट, चिंता मत करो, ये नोट्स मैं अपलोड करूंगा जैसे ही लेक्चर खत्म हो जाएगा, उसके बाद मतलब टॉपिक खत्म हो जाएगा उसके बाद you will get to know the equations, but the thing is the in between matter, how you are achieving it, that you will not be able to understand if you are not attending the lectures. So now what I request you is, please write down variations of hybrid pi parameters. Variations of hybrid pi parameters. I am saying this thing. I hope my screen is clearly visible. There is a
yes, sir.
table which represents the variation in various parameters of hybrid pi model. Now, we know that VCE is increasing. I repeat, we know that VCE is increasing. As a result, the base width, effective base width is decreasing. Effective base width is decreasing. So please note down this point. You have to draw the table, but I will let you know when. Initially, what you need to do is note down this point, that increase in VCE would lead to decrease in effective base width. Decrease in effective base width. I hope you have written this line, that increase in VCE leads to decrease in the effective base width. Now, the next point is the dependency of RBB dash. The dependency of RBB dash with IC and temperature, with IC, collector current and the temperature is present.
Sir,
Now,
can you repeat?
yes, spreading resistance. What is the spreading resistance? Hello? What is the spreading resistance? Hello? I was audible, I know that. So I'm just asking, what is RBB dash? What is the spreading resistance?
सर RBB डैश आपने बोल दिया.
Sir, I'm asking the definition basically. What is RBB dash spreading resistance? बोला तो है पर. Any student, what is spreading resistance? Very good. Okay. So the dependency of RBB dash with IC, the dependency of RBB dash with IC and temperature is present. Now, the decrease in RBB dash, the decrease in this resistance with IC is due to conductivity. The decrease in RBB dash with respect to IC is due to conductivity. Now we all know that the base spreading resistance is between the base and the virtual base, that is B and B dash, and IC is the output collector current. So the decrease in RBB dash, the decrease in the input resistance would lead to what? At the output side, that is at IC side, it is due to conductivity. Okay. Now proceeding further, the modulation of the base with increase in IC is nothing but shown in the table. Modulation of base with increase in IC is shown in the tabular form. So these are the various parameters which are going to get affected or varied with increase in IC, increase in VCE, and increase in temperature. Can I proceed further?
Yes, sir.
Okay. Now we are talking about CE short circuit current gain. CE short circuit current gain. So I request all of you to kindly draw this diagram. Please, all of you are requested to draw figure number 7 and figure number 8. If the figure is not clear, please let me know.
It is clear, sir.
Once you draw the diagram, then let me know so that I can proceed further better. Okay, Manshu.
Yes, sir.
Yes, students, I hope very soon you would be able to complete the diagram. Once you complete, I repeat again, please inform me.
Done, sir.
Done, sir.
Done, sir.
Completed.
Okay.
Done, sir.
Please note down short circuit current gain. Short circuit current gain would be when RL is equal to 0. When RL is equal to 0. That means single stage CE amplifier
सर सिंगल क्या?
सिंगल स्टेज सीई एम्पलीफायर. आपने टू स्टेज का आरसी कपल्ड पढ़ा है, तो ये सिर्फ सिंगल स्टेज रहा, लास्ट पार्ट मतलब सेकेंड पार्ट ऑफ आरसी कपल्ड कैस्केड का. सो सिंगल स्टेज आरसी कपल्ड Okay, चलिए. Now we are going second point. Please note down the second point. To obtain frequency response of hybrid pi model. To obtain frequency response of hybrid pi model. Now DC voltage is reduced to 0. RL is already 0. तो ये जो सर्किट बना है आपका फिगर नंबर 7 का जो सर्किट है उसमें हम लोग क्या देखेंगे, ये जो आर बी डैश सी दिख रहा है ना, आर बी डैश सी, ओके गाइस, देयर इज वन चेंज. ये जो सीसी दिख रहा है आप लोगों को, हेलो,
हाँ सर.
Yes, sir.
एक रेजिस्टर को कनेक्ट करना है बिटवीन सीई एंड आरसीई. कनेक्ट वन रेजिस्टर बिटवीन सीई एंड दिस, लाइक दिस. डू नॉट जॉइन इट ओवर हियर, जॉइन इट ओवर हियर. ऊपर से ऊपर, यहां से ये ऐसे करते हुए यहां पर ये एक रेजिस्टर से ज्वाइन कर दो. और इसको
At the junction or little before the junction?
it should start at the junction, but it should not end at the junction. It should end before the junction.
Okay, sir.
And label that resistor as RB dash C. Label that resistor as RB dash C. Now I hope you have drawn the resistor between from the junction point, that is at CE, before RCE, labeled as RB dash C. So now the thing is, since the DC voltages are reduced to zero, RL is already equal to zero. RB dash C, the resistor that you have drawn, can be neglected because of its very high value. RCE, RCE is already short circuited, and CE and CC, CE and CC, both the capacitors appear in parallel. Appear in parallel. So we have drawn the modified diagram of figure number 8. I hope now it is clear to you how the figure number 7 has been modified to figure number 8. Please note that IL, please note that IL is equal to IL is equal to minus GM multiplied by VB dash E. IL is equal to minus GM multiplied by VB dash E. Secondly, we know that RB dash E and CE plus CC both are in parallel. Both are in parallel. So let it be written in the form of Z. Let it be written in the form of Z. Now GB dash E, GB dash E is nothing but GM upon HFE. Can we retire from this formula? We know that HFE is equal to GM into RB dash E, and 1 upon RB dash E is nothing but GB dash E. So GB dash E is equal to GM upon HFE. GM upon HFE. Now VB dash E, voltage between base and emitter, VB dash E is equal to II into Z. Jo, voltage at this particular point, are you able to see voltage at BE, VBE? Height,
Yes, sir.
Yes, sir.
voltage at this particular point, or modified version, voltage at this particular point, B dash and E, B dash and E, voltage at this particular point, VB dash E is equal to the input current II, and multiplied by this total impedance. This is nothing but Z. This is nothing but Z. Okay. So VB dash E is equal to II into Z. Now we are going to put all the values. You know that Z is nothing but this parallel to this. We can solve it out, yes or no? Hello.
Yes, sir.
So what is the impedance of a capacitor? Hello. Yes. Enrollment number 17, 17. Hello. I think I'm audible. Yes, ma'am. Ma'am, what is the impedance of a capacitor? Hello. Hello, ma'am. It is j omega c. Xc, it is equal to j omega c. So we will put this value over here. We will try to solve these two things, and we will find out what is VB dash E. So please let me know the final answer of this particular formula. VB dash E is equal to, after putting the value of Z. Are you getting this thing? Students,
Yes, sir.
now what is current gain? 17. Enrollment number 17. Formula of current gain. Hello. Antara, are you able to hear me, beta?
Yes, sir.
बेटा करंट गेन का फॉर्मूला क्या होता है? हेलो, हेलो, enrollment number 59.
Yes, sir.
What is the formula of current gain? $59.
Sir, am I audible now?
You are audible.
Hello.
Yes, you are audible, Antara.
Is it IC upon IB formula for
I am actually
current
talking
gain?
about figure number 8. So according to figure number 8, what is my current gain?
I upon IE.
बेटा फिगर नंबर 8 आपको दिखा, आपने ड्रॉ किया था,
Yes, sir.
तो उसमें आउटपुट करंट क्या है बेटा?
I.
आउटपुट करंट
IL.
इट्स हाँ IL. इनपुट करंट
II.
हाँ, तो करंट गेन का मतलब क्या होता है? आउटपुट अपॉन
Input.
तो IL अपॉन IL.
I. Current gain.
Very good. So as per the discussion, we can say that current gain is something like this. So from this equation, we are going to calculate IL upon II. In case of any doubts or any queries, please feel free to ask. If there are no doubts and no queries, that means you are clear with this terminology. So can we proceed further? Yes, students, are you getting this thing? So please calculate IL upon II and let me know the final answer. Yes, enrollment number 52. Hello, enrollment number 52. I think I'm audible to you. Enrollment number 52, yes or no? Please reply. Enrollment number 52, are you there in the class? Hello, enrollment number 53. Are you there in the class?
Yes, sir.
Beta, what have you got in form of IL upon II from this equation?
Minus GM RB dash E upon 1 plus J omega RB dash E CC plus CE.
Okay. So this is nothing but the formula of AI. Okay. As Antara has just now told that AI is nothing but IL upon II. So if we take this II over here, what is the remaining thing that we have calculated? So that is reflected in this particular format. Just wait a minute. Yes. So we have got this AI, which is nothing but IL upon II, which is nothing but minus GM divided by G B dash E plus G omega CE plus CC. This is my AI. This is my AI. Now I want to calculate F beta. F beta. What is this F beta? F beta is the frequency range for the bandwidth of the circuit. F beta is the frequency range for the bandwidth of the circuit. F beta is equal to Gb dash E divided by 2 pi Ce plus Cc. Now, over here in the circuit, we are having various terminologies. So, based on this, we can say that 1 upon HFE multiplied by my transconductance. 1 upon HFE multiplied by my transconductance is equal to, upon this is this. આ ફોર્મ્યુલા ક્યાંથી આવ્યો? આ ફોર્મ્યુલા અહીંયાથી આવ્યો છે. This formula has come from this particular equation. That is Gb dash E is equal to Gm upon HFE. So we are replacing this thing over here in this particular format. Gb dash E ne 1 upon HFE and a Gm, because it is nothing but 1 upon Re and the rest of the things can be resolved. I hope you are understanding it, guys. Please let me know in case of any doubts or any queries. Hello students, please respond in case of any doubts or any queries. Hello students.
No, sir, no doubts. And hello,
Yes, hey.
sir, no doubts regarding.
Okay. Okay. So I would like to complete this article. This article is completed within this page. So I would request you to kindly note down. We know that omega is equal to 2 pi f. And we put this formula of f beta. Hence, at f is equal to f beta. At f equals to f beta, my AI becomes 1 upon root 2, that is 0.707 of its lowest frequency value for HFC. For HFC, AI is equal to 0.707. This frequency range is for the bandwidth of the circuit. Value of AI at omega or at W is equal to 0 is minus HFE. At omega is equal to 0, AI is minus HFE. In agreement with the definition of minus HFE as the lowest frequency short circuit CE current gain. So the lowest frequency of short circuit CE current gain, the article that we started, it is denoted by minus HFC. Hence, AI can be termed as finally in this particular format. So this equation clearly represents that the current gain is inversely proportional to frequency. Current gain is inversely proportional to frequency. That is, lower frequency to the denominator is less than 1. AI would be approximately equal to HFE. I repeat, at lower frequencies, denominator would be less than 1. At lower frequencies, denominator would be less than 1. AI would be approximately equal to HFE. So as the frequency would increase, the current gain would decrease. Now that is the breaking point for our subject of analog circuit design. That is how the transistor is going to react at higher frequencies. We have analyzed from these equations that the current gain is decreasing with increase in frequency. So if my frequency is increasing at that particular moment, the CE amplifier gain, which is current gain, is decreasing, which is not feasible for any of the amplifier concentration circuits. Why and how is the decrease? That is being reflected in this particular graph. I hope figure number 9 is totally clear to all of you.
Yes, sir.
We will start the discussion on figure number 9. Figure number 9 is the graph between the current gain and the frequency. It is the graph between the current gain and the frequency. The fall in the graph is because of the 20 dB per decade downfall. 20 decibel per decade downfall. That
Yes.
decade downfall you have already studied in control systems as well as in network theory subject. So you are already aware what is 6 dB octave, what is 20 dB decay downfall,
Yes, sir.
what is 3 dB fall, etc. So there is no need to explain what is the fall, but there is a need to understand that there are two crucial points over here. One is log f beta and another one is log ft. One is log f beta and another one is log ft. So these graphs would basically reflect these two particular points or two particular crucial areas, log f beta and log f of t. Log f of t or f of t is nothing but commonly known as unity gain frequency. I repeat, f of t is known as unity gain frequency. As the value of HFE is greater than 1, FT would get affected. As the value of HFE is greater than 1, the FT would get affected, as a result of which FT would be approximately equal to HFE into F beta. Ft would be approximately equal to HFE into F beta. Hence, it is equal to this. Where we already know that CE is greater than CE is greater than CC. Hence, CC can be neglected in this terminology. The modified formula would be GM upon 2 pi CE. GM upon 2 pi CE. Ft, as I told, is the value which depends on the operating condition. Ft depends on the values of the operating condition of the transistor, and it is also dependent on the output current, that is collector current. So Ft is equal to HFE into F beta. It represents short circuit current gain bandwidth product. Value of Ft is 80. I repeat, value of Ft is 80 megahertz. 80 megahertz. The value of F beta is 1.6 megahertz. 1.6 megahertz. Since the value of Ft is 8080 megahertz, F beta is 1.6 megahertz. So Ft is nothing but transconductance divided by 2 pi Ce. So please note down the last line of this article. I request all of you to please note down the last line of this article. That is the gain bandwidth product. I repeat, gain bandwidth product is always constant. So two transistors can have same f of t. Two transistors may have equal f of t. Then the transistor with low HFE will have a higher bandwidth. If the two transistors would have same f of t, so the transistor with lower HFE. So how can we know the lower HFE? Based on the data sheet. So the transistor with lower HFE will give me a good bandwidth, will give me a higher or a good bandwidth. Okay guys, so that's all for today's lecture. In case of any doubts or any queries, please feel free to ask.
Hello, sir.
Yes, beta.
Sir, can you repeat the last line?
Yes, the gain bandwidth product is almost constant or is always constant if the two transistors have equal f of t. If the two transistors have equal f of t, then transistor with lower HFE will give higher bandwidth. Transistor with lower HFE will give higher bandwidth.
Okay, sir. Done.
Any other doubts? Please let me know. Fine, guys. Now there are few announcements. Any particular Monday? Morning? Prayer time. Okay, students. So the few announcements are 1D11 batch. 1D11 batch. Hello.
Yes, sir.
Your
Yes, sir.
lab EMI, electronic measurement instruments, which is planned on Saturday, at 9:30, would be taken on Monday 9:30. 1D11 batch EMI lab of Saturday would be taken on Monday only for this Saturday. Is it fine?
Okay, sir.
Okay, sir.
Okay, sir.
9:30 to 10:30, 1 hour lab would be conducted instead of Saturday's lab. Secondly, you are having a lecture at 11:30 for my subject 3141002. Yes or no?
Yes, sir.
That lecture would not be conducted. It is rescheduled and I will inform you at a later stage. So there is no lecture from 11:30 to 12:30. Okay?
Okay, sir.
So Merry Christmas to all of you. Have a nice weekend and we will meet in the next week. Have a
Merry
nice day.
Christmas to you as well, sir.
Thank you, sir.
Thank you,
Okay.
sir.
Yeah.
Thank
Thank
you.
you, sir.
Thank you, sir.
Thank you, sir.
Yeah.